So in the previous lecture, we started with a differential pair, and what I told you was giving an example of an ECG measurement where we would like to remove the common mode signal and only measure the differential signal between the two inputs, positive input and a negative input. And that is one of the most critical functions of analog circuits because it removes the common mode noise. Generally, these common mode noises, for example, a hum due to the power line, these are so large that they can swamp out your sensitive amplifiers. So we would like to remove these large signal inputs before even they get amplified at the source itself, and that's where the differential pair comes in to help. Other thing I did not mention yet is what am I doing? Why are we doing all these things? We talked about current sources, we talked about differential pair. So I kind of hid that information from you so far, but I think from the questions it's clear that you really need to know the motivation for all these things. So before, just at the beginning of the course, we started with an op-amp design, if you remember. Now things will be clear, because what we are trying to do is build an op-amp, and you use the op-amp in your lab. At that time, we talked about op-amp as a black box which will amplify differential voltage between the two inputs, if you remember that. Now suddenly things will fall in place. Also, we need large gain, so we are trying to figure out how to get large gain. So today's lecture will be continuation of using the differential pair and then analyzing it further. And during the op-amp experiments, you were exposed to various terms like common mode range or common mode rejection ratio, or input DC offset voltage or DC offset current. So all these things we are going to slowly start looking at from the device point of view, meaning the transistors which make up the op-amp, and then slowly we will build to the final thing, which is an op-amp, by end of these next couple of lectures. All right, so let's get back to our blackboard. In the lecture, I talked about virtual ground. Again, it was a little bit hand-wavy explanation, but it was just to get you warmed up to the idea. And in this particular lecture, we will kind of walk through that in detail. And this particular concept is used in many circuits, and you should learn how to identify them so that the analysis part becomes easier. So let's draw a simple diff pair, which is MOSFET based, output load resistors. And you should also practice drawing all these circuits. I've been telling you over and over again, because once you start drawing them, then you will be able to quickly understand them better too. So here is our diff pair. These are two output resistors RD, transistors M1 and M2. When you apply voltage VCM at the input, okay, this is VCM. And this is also VCM, let's say, and so then we know that the output is going to be biased at, if this current is too high, then the output will be biased at VDD minus I times RD. So both outputs will stay at that. Now let's say I apply a voltage delta V, which is going from VCM to plus delta V, by plus delta V. So this is a delta V steps, okay, and then on the other side I'm going to apply a step which is VCM minus delta V. I'm applying a common mode voltage of VCM, that is not changing, and then I'm only applying differential input, which is plus delta V on one side and minus delta V on other side. So this is a fully differential input that we are applying, and we are trying to figure out how this diff pair behaves in presence of differential input only. And then based on that we can figure out how to quickly analyze the circuit. Let's call this node tail. As I said, this 2i is called the tail current source. the tail node, we expect, let's say, we don't know right now. Let's say originally it was sitting at V tail, and let's say it moves up by delta V tail. We don't know if it will or not, but let's just assume for the beginning that it moves up by delta V tail. What we are trying to do is we are zooming in around VIP minus VIN equal to 0. If you remember that transfer characteristic, this was your VIP minus VIN that we did last time, and this was your V out, right? Or delta I. We are trying to look at this particular part of the curve where a difference between the two inputs is very small. So originally, as I said, VIP is equal to VIN is equal to VCM, and then we are applying delta V going up to VIP, delta V going down to VIN, and then we are assuming V tail that will move to V tail plus delta V tail. And we are trying to figure out what is this delta V tail is going to be. What is the original equation? Basically, if you look at the current in the two branches, M1 and M2, that is going to be the sum of the two together will be equal to 2I. So ID1, which is the drain current of transistor M1, plus ID2 is equal to 2I. Because that's the way we have a current source of value 2I on the bottom, right? If this is the case, then ID1, we expect it to move up by some current delta I, and since the summation of these two is 2I, then ID2, which will be originally I, which will become minus delta I. What we are thinking again here is the transistor is behaving just like a transconductance, and we are ignoring R out effect. Since it's behaving like a transconductance, for delta V input, we expect the drain to source current of the transistor M1 will be equal to GM times delta VGS, right? Delta ID1 will be equal to delta I, this comes from here, and that will be equal to GM1 times VGS. What is the VGS? VGS on the gate we had delta V, and on the source we said that, oh, I have delta V tail. Okay, that's the change. So that's the current delta I. Similarly, we can say delta ID2 is equal to minus delta I. Okay, from this, and that will be again given by the transconductance GM2, delta V which is applied, which is minus delta V we are applying at this input, so minus delta V, and again we are saying here delta V tail. Again, this is we are looking for VGS, okay, gate change and source change. So we are looking at the transconductance transistor as a transconductor of value GM. So if you agree with that, then as you can see, the two currents have to be equal and opposite, right? Since M1 and M2 are identical, we can say GM1 equal to GM2 is equal to GM. We can say delta ID1 is equal to minus delta ID2, and that will give us GM times delta V minus delta V tail is equal to GM2, and here since we are taking the negative sign, this will become delta V, this will become plus delta V tail. This happens because of this negative sign. Now quickly you can see this delta V is the applied input delta V. This tells you that, hey, delta V tail has to be equal to 0. You can clearly see now that the tail node doesn't move even when you apply a differential input, only when you apply differential input. Let me take that back. Okay, if the common mode voltage is held constant on both sides, and then you only apply differential input, then the tail node or the common source node between the two diff pairs, between the two transistors, that doesn't move. That's what this is telling us. Also, you can see that if you remember, let's say you have two resistors, okay, R and R. All right, and if I this looks like I apply delta VDM divided by 2 on one side and minus delta VDM on other side. So if you do that, then this particular center node doesn't move. So this delta Vx will be equal to 0. Okay, it will not change. So what we say that is node X acts as a virtual ground. Virtual ground because it's not like that node is connected to ground. It behaves like a virtual ground. And in this particular case, if you see the current which is flowing out here, okay, cannot get through this current source, so it has to go back up this way. Okay, so there is no current flowing since this is a current source. There is signal current cannot flow into the current source. Okay, the current source is a constant bias current. So this particular node, the tail node, acts as a virtual ground. Now this simplifies our analysis quite a bit. Okay, and let me explain how so. The same analysis, you can do it for the BJT diff pair on your own also, and the same analysis holds true. So I'm going to go back and forth between BJT as well as MOSFETs, but I may not cover, if the analysis is identical, then I may not cover the exact same analysis for each case, because it's a lot of repetition and you might just get bored and fall off your chair. Let's keep it interesting, but you should manually try to do it yourself, analysis for each type of device. Some cases there are nuances, there are differences, so there I will definitely do both the analysis to show you the difference, and you will see what I mean by that. Okay, so now we can utilize this analysis for this half circuit concept for BJT diff pair. Let's draw the diff pair. In this case, we'll start with the BJT. And what we said is this node, the tail node, is a virtual ground. And this is virtual ground only when you apply differential signal. Okay, this is critical. Only when you apply differential signal. So now we are going to analyze this particular diff pair for differential signals. So we can, since this is a virtual ground node, we can kind of connect this to ground for processing ourselves, and then the circuit becomes simple. Since I said kind of, I would just use a dotted line here, and then here is this is the virtual ground, and then this would be, so this is VIP, this is VIN, RC, RC, and this is VON, this is VOP. Now here we can analyze that VON will be equal to minus GMRC VIP, which is equal to, since we are applying this case, we are applying delta VDM divided by 2. On this side, we are applying minus delta VDM divided by 2. We can write this expression. This will be equal to VON will be minus GMRC delta VDM divided by 2, and VOP will be equal to minus GMRC and VIN, that will be equal to minus GMRC, and this will have minus delta VDM divided by 2. So if we look at VOP minus VON divided by VIP minus VIN, which is our voltage gain, and what would that be equal to? This you can clearly see it will look like GM times RC. Note that GM is the transconductance of a single transistor, each transistor. Alright, so here we would say Q1 and Q2. Q1 and Q2 both will have same GM, which will be I divided by VT. So this will look like I divided by VT times RC, correct? And this we have done it before, because this IRC is the voltage drop across this resistor. And then VT is 26 millivolts. So from this we can calculate the gain. This analysis holds true when we are doing analysis for differential input signal. Now we need to figure out what happens for common mode signal also, because a real signal will have both common mode signal as well as a differential signal, and we can apply superposition to both and then figure out the combined response, right? So in this particular case, we only applied differential signal, and we figured out that the tail node looks like a virtual ground. So then I can simplify the circuit as shown over here. Okay, and then we calculated the gain to be GM times RC. And note that we did not have negative sign here, because we have already, the negative sign has been taken care when we label the nodes. Okay, for example, if this is VIP, then this is labeled VON. So the inversion is already taken into play. Alright, so now let's analyze what happens when we apply VCM. So for common mode response, so we are going to look at common mode input voltage change. What happens there? So let's draw the circuit again. It's important to draw the circuit so that you get a feel for each signal, how does the circuit behave, since there is a difference between the two. 2I, this is VCC, RC, RC. So now we are going to apply delta VCM to both sides. The VCM moves by delta VCM, but since it's a common mode signal, both sides will move, right? So we need to figure out what happens at the output. It should be fairly obvious to you that since this is a constant current source 2I, both inputs either move up or down together, the current flowing through each transistor still stays same I, and that doesn't change because this is a current source. So you can pretty much tell that delta VCM input VOP equal to VON will be always VCC minus IRC. So it doesn't matter what delta VCM we apply, as long as all the transistors are in active region, we are maintaining them, then the output doesn't change. The common mode output voltage doesn't change. Okay, it always is fixed by this. So definitely then we can say that, hey, the common mode gain is equal to 0. Okay. Now the key part here is that you need to realize that we are assuming that the current source 2I is ideal, so it doesn't have any output resistance. Okay, so this is the only time this will look perfect. Let's imagine a current source with, we will do the same analysis with current source output resistance. I'm going to intentionally make it RE divided by 2, and you'll know why I'm choosing RE divided by 2. Okay, not RE. I'm going to redraw the schematic again, and I would appreciate it if you could redraw it too. So this is our VCC. Let's use some color. And as I say again, in analog circuits is all about intuition, and it's all about how you draw your schematics. So if you draw your schematics well, then it will be very quickly you can analyze the circuit. So in this particular case, since I'm saying it's RE divided by 2, I'm going to make it look like two resistors of RE parallel RE. Intentionally. Originally we had 2I current, so I'm going to draw the current each on both sides, and then now you will realize why I was using 2I and not I. And then each current source will have a resistance, output resistance of RE. So this is I, this is I. I'll give you a second to think about it. So what I'm doing now is I'm applying delta VCM, and here also I'm applying delta VCM. And what I'm looking for is what happens to my VON and VOP. So I'm applying common mode input, and I'm changing the common mode input, and I would like to see its impact on the output voltage. All right. It should be really obvious to you by now that this circuit, I can chop it off right in the middle. Okay. So the input is same and everything is same. Okay, on both sides of the circuit. So I can only analyze half the circuit, and the same thing you should see on the right side also. Okay, so analyzing half circuit means we will have to just see this. This is what it looks like, RE, this is your RC, VCC, and this is VON. And this is where I'm applying delta VCM. What does this circuit look like? Okay, this circuit that I have drawn here as a half circuit. If you remember early on when we were talking about single transistor circuit, this circuit looks like a common emitter amplifier with emitter degeneration, right? This is your emitter degeneration. You can look at lecture 18 for this. If you feel that you've forgotten, then you can look at lecture 18 for the analysis. But I'll just take the result and show you the result here. In this particular case, since I have this emitter degeneration resistance, then my VON divided by VIP, which is kind of V output common mode voltage divided by V input common mode voltage, right? Because I'm applying a certain common mode input voltage, and then you get output common mode voltage, right? So this is called common mode gain. And what is that equal to? If you go back to that particular lecture, and you will see that it's GM divided by 1 plus GM times RE, and then that gets multiplied by RC. So this is kind of an effective GM, if you remember, of emitter degenerated transistor actually. let's say if GMRE is much greater than 1. As you can see, this is a current source. So the current source is supposed to have really high output impedance, output resistance. So obviously you should expect the GMRE to be much greater than 1. So in that case, we can simplify VICM is equal to minus GM divided by GMRE and times RC. So GM will go away, and this expression will just look like minus RC divided by RE. What does this tell you? What is the insight here? The insight here is that, hey, if my current source is of good quality, which means my current source output resistance is high, then my common mode gain, which is V right here, VOCM divided by VICM, that should be much less than 1. So VOCM divided by VICM should be much less than 1 if RE is really large. And this kind of makes sense, right? If you have ideal current source, RE will be infinite. And then your common mode gain, as we just went through the analysis before, it was 0. Coming back again, if you remember, our goal is to only let the differential signal go through and stop the common mode signal right at the door. That's our goal by using a differential pair. And if you look at this analysis, if the quality of your current source is good, then you can definitely do that. Now, this identical analysis is applicable for MOS diff pair, exact same analysis, so there is no change anywhere, and you can do it yourself and convince yourself, and let me know if you have any questions. Now, I would like to introduce you to a new concept, CMRR. This is called common mode rejection ratio. Let's start with a simple block diagram representation, plus, minus, and here is your output. So at the input, we are applying VCM plus VDM divided by 2, and at the other input will be VCM minus VDM divided by 2. So, and then say this is your output, V output. So this is this particular amplifier in this particular case is differential input and then single-ended output. This is important because I'm going to compare the two cases so that you can represent this accurately. Many people get confused between the two cases, which is single-ended output versus differential output. So let's go through the details. So the output here, V out, will be equal to ACM times VCM plus you will have ADM times VDM. So it's a superposition theorem that we are using. Whenever you apply VCM, then you will get common mode gain ACM, and if you apply only differential signal, then you will get differential gain ADM along with the differential signal. So this part, if you remember from the examples that I told you earlier, is the undesired portion, and this part is what we desire. So common mode rejection ratio is it quantifies the ability of an amplifier to reject the common mode signals. So it's given as CMRR is equal to ADM differential gain divided by ACM as a ratio. And if you want to look at CMRR in dB, which is the way it's always measured, is 20 log ADM divided by ACM. And the reason we take mod is we don't care about the inversion or negative signs anywhere in this analysis. Let's see what's the significance of this, right? So a good amplifier, let's say the one you're using for ECG measurement or some other measurement of sensitive signal, then you want the differential gain to be as high as possible and common mode gain to be as low as possible. So this number has to be as large as possible, CMRR. So CMRR of 10 means, let's say CMRR of factor of 10 will give you 20 dB. And so we want the CMRR to be as high as possible. This is okay when you're looking at only single output, okay, one output. What happens when you have a fully differential amplifier? Let's go through that as well. So what does fully differential or amplifier with differential outputs? So when you have an amplifier with differential outputs, there is a small nuance that you need to take care of. And VIP, VIN, this is minus and plus. So this would be VON and this is VOP. Again, I'm applying the same input, which is VCM, VCM plus Vd by 2 minus Vd by 2. Okay, same as before. And what you would see at the output, VO P and VON, is you will see this expression, VCM, ACM times VCM, and then you will see ADM, and then you will see VDM by 2. Same thing over here, ACM, VCM plus ADM, and here you'll have VDM by 2 minus VDM by 2. The point here is, interestingly, I think I have made a mistake. This should be negative and this should be positive, because this is the positive output. And then on top of this, you will see something called ACM DM times VCM. And here you will see minus. Let me do the signs again. This should be minus, should be plus. ACM DM VCM. This may look complicated, but hang on, I'll peel it slowly for you. So what does the first term mean? First of all, let's go through this. In the single-ended case, when VCM went up, the output also moved, right? We are only applying VCM and the output is moving. Now, when I'm using the single-ended amplifier, I have no way of telling if I have a differential input or common mode input just by looking at a single output. If V output moves because of the common mode signal, then it's going to corrupt the signal that I'm going to sense, because I only have one output, and that output I'm expecting that only VDM should make a difference. So in this particular case, the ACM, which is common mode gain from both the inputs to the output, becomes undesired. Now in this particular case, what will happen is, when we have differential outputs, is if this VIP and VIN both move up by, let's say, a certain value. Let's pick a number. Let's say both move by 10 millivolts. And now, because of the common mode gain, ACM, this will move up and will also this move up. Both of them will move up because of just the common mode gain, each output. So then we have both outputs moving because of the common mode gain only. When you look at the differential signal though, when I'm looking at differential signal, we are only looking at the difference between these two signals now, since I have two outputs. Any common mode movement at the output, since I have a differential output, it doesn't really bother me. Any future amplifier will reject this signal, because if there is a next amplifier which is cascaded, which is also a differential amplifier, this part will be rejected by next differential amplifier. And what is this really doing? So a small variation because of the input common mode change will only change the bias point at output. If the bias point changes too much, then it may impact your small signal gain of the next stages. Also, if both sides move up or down by substantial value because of common mode signal, then you could also have reduction in your output swing. However, all in all, the common mode gain in case of a fully differential amplifier means differential inputs and differential outputs. It's quite innocuous, this ACM part, because I'm changing common mode inputs up and down, and the output common mode also changes up and down slightly with whatever common mode gain we have. In the previous case, even that slight change would be a problem, because I don't have a way of differentiating between if my output moved because of common mode signal or differential signal. In this particular case, I do have the luxury because I have two outputs, and the next stage will again look at the differential signal between the two, and the common mode part will get rejected further. So the differential part is pretty obvious. Okay, the differential gain part is obvious. Now let's look at this last piece. What does that tell you? Here what I'm saying is, this is common mode to differential mode conversion, which means that when I am applying a common mode signal, the output acts as if there is a differential signal. And clearly, if you see, this is common mode to differential, and the sign here is negative and sign here is positive, just like there is a negative and positive sign over here. You can say that for differential signal, it's the common mode to differential differential mode gain, that's important. Because if this particular gain, and I'm going to tell you how that comes about, if there is a common mode to differential mode conversion, then my output signal is corrupted. I will not be able to tell my differential signal from common mode signal. in case of differential amplifiers, fully differential amplifiers, it's the common mode to differential mode gain that is important. And we are going to go through a few examples, so it will be very distinctly clear for you. So why does this happen? Why would you get common mode to differential mode gain? The most important reason for this is when we do circuit design, we assume everything is identical. All devices are identical, all resistors are identical, everything is identical. Unfortunately, that's not the case when you actually implement it on a chip, or if you take different components from markets and put it together, right? Because each device will have some mismatch with the neighboring device. So mainly due to asymmetry, circuit asymmetry, or we call this mismatches, we get this common mode to differential mode gain. So in that case, then the common mode rejection ratio is defined as, for differential circuits, is defined as ADM divided by ACM DM, or also 20 log ADM divided by ACM DM. If I just use ACM over here, ACM really doesn't make a dent in my differential signal in case of fully differential signal. And that's the key important point I'm trying to drive over here. It's the ACM to DM, which is common mode to differential mode conversion. That's what matters. Also, that happens only because of mismatches in the circuit. So now let's go through a few examples, and then it should be clear to you how these two factors are to be taken into account. We'll take the first CMRR example, which is, in this case, first we'll analyze a single-ended output, which is a circuit that looks like this, plus minus and one out. So we'll take the same circuit. We have one resistor. I'm going to use MOS here. And if you remember this, we put in 2I. And what was the resistor value we use? We use RS divided by 2. For bipolar, we use RE divided by 2. For MOSFET, we are going to use RS divided by 2 because it's a source. Here is M1, M2, and here is RD, and this is your VDD. And let's say that I'm only looking at one output right here, VO, and this is your V. If this is my output, then obviously this input is VIN now, and this is VIP. We are only looking at one output. So what is ADM in this case? Differential mode gain. That will be, if I'm looking at two outputs, then the differential mode gain was GMRD. But since I'm only looking at one output, it will be, differential gain will be GMRD divided by 2. Why this factor of 2? You should convince yourself. Now, what is a common mode gain? ACM in this case. So if you remember, we did the common mode analysis. We split the circuit in factor of 2. And in this particular case, we have source degeneration. With the source degeneration and with the approximations that we did, this should look like RD divided by RS. In bipolar case, it came out to be RC divided by RE, if you remember. And we said that if the current source is good, which means that RE is very large, then this ACM would be very small, should be small. Okay. Similarly, if the RS is large, which means that this current source is perfect, ideal, then ACM will be close to 0. So now let's, in this case, figure out what is our CMRR. CMRR is given by 20 log ADM divided by ACM, which is equal to 20 log GMRD divided by 2 times RS divided by RD. RD goes away. CMRR will be 20 log GMRS divided by 2. Your common mode rejection ratio would be large if your current source is ideal. RS is as large as possible. So this is what your expression for common mode behavior would be. Now let's take the point of differential output. Okay, so we have differential input and differential output. We'll use the same circuit. Things get really interesting when we use differential output. Since I said in the previous lecture, if everything is matched, if all the devices are identical, then you will never get any common mode to differential mode conversion. So only when there is a mismatch on either side, then you will start getting common mode to differential mode conversion. So let's assume that only resistors are mismatched. Okay, so here we have RD and this is RD plus delta RD. So this is your VOP, this is your VON, and VIP and VIN, M1 and M2. If we consider what is a common mode output for both sides now, let's see VON divided by VIP, and this is only happening for common mode signal. is equal to, what was the gain? If you remember, this was a source degenerated amplifier, right? So then this is going to look like minus RD divided by RS. And on the other side, it will look like VOP divided by, what is the mistake I have made here? VOP, sorry, erase this part here. This should be VIP and this should be VIN, and we are only looking at common mode. So in this case, since I have, instead of RD, I have minus RD plus delta RD divided by RS. Okay, so I'm just figuring out. So now you can clearly see that common mode, if both the inputs go up, let's say, the output on the left will drop down, but the output on the right will drop down further. And now you can clearly see that because of the mismatches, that there is a differential signal at the output which is generated because of this delta RD. What is the VOP minus VON divided by VCM? And this would be your ACM DM. This is differential output and this is common mode input. Common mode, and this is your differential. Let's write that. So what would that be? That would be equal to, if you subtract these two, then you should get minus delta RD divided by RS. So this is our common mode to differential mode gain. So now in this particular case, what would be our CMRR? Common mode rejection ratio will be 20 log ADM divided by ACM to DM, and that would be equal to 20 log GMRD divided by delta RD, and that gets divided by RS. What does that? We will rearrange that so that we are familiar. This should be 20 log GMRS divided by delta RD divided by RD. What does this tell us, this expression? If you compare the previous expression, right, that expression also had GMRS. So RS has to be large, first of all. Okay, if the RS is infinite, then we don't have a problem. Okay, but RS will be finite. So in that case, how well the two transistors match? If delta RD is really small, 0, then again we don't have a problem. The CMRR will be infinite. But in reality, you can get delta RD divided by RD, which is resistor matches. The degree of matching is important. So we can get this to be less than 1% easily. You can see that if the two resistors match very well, the two transistors match very well, then you should get a very good common mode rejection ratio. The concept I'm trying to drive to you is a really simple concept, even though it feels like we kind of belabored on this for a long time. Is we have a single-ended amplifier, single-ended output amplifier, and then we have a differential output amplifier. The differential output amplifier has much better performance if you're able to match both sides very well when it comes to the common mode rejection ratio. This number will be, you can achieve a very good number there. So in this particular example that we just did, right, we only considered the resistor mismatches. Now in reality, we will have mismatches from all over the map, right? So then you have to consider them also. So you have to look at the transistor mismatches. These two transistors will mismatch, and then you have to add that into picture also. We will stop right here.